So thank you for the opportunity to speak here. This is the last talk, so I think we should thank the organizers and the staff who have made this event possible. So I'm going to talk about a Markov chain, and it's going to be pretty simple Markov chain. So it lives in 0, 1 to the n. And so I have my configuration might look something like this. These represent the ones. And at each stage, so this is contained in the natural numbers to the n. So at each stage, I'm going to do two things. First, I'm going to add a particle. And then, like in Carolyn's talk this morning, I'm going to stabilize. I'm going to use a different stabilization rule, but I will do that. So my rules for stable are there's at most one particle at every site, which corresponds exactly with what Carolyn was talking about this morning. So what we're going to do is, and here, so I'm someone who believes in the flat Earth theory. I also believe in that Earth is one-dimensional. So I've been working on this problem for about 16 years, and we're supposed to get beyond 2D in this conference. I still haven't made it to 2D after 16 years, so everything I will be talking about today will be one-dimensional. So I'm going to put a sink at 0 and a sink at 6 here, so n is equal to 5 in this example. And at the first thing I'm going to do is I'm going to choose a random location and add a particle. And then I'm going to stabilize. OK, and this time I'll choose 1 as my location. And so now I have this configuration here. This is a stable configuration because there's at most one particle in every site. And then the next time what I can do is, so choose this here. And then what happens, so now if I have 2 particles at a site, then 2 or more particles at a site, then 2 of those particles will take a simple random walk step, and those steps will be independent. They will be independent of everything that's happened previously in the system. So what might happen here, so this particle moves here, this particle moves here, then what do we get? OK, now this is still not stable. I've got 2 particles that are at 1. What happens? So again, I will have, this should be conservative. There should be the same number of particles. So now, yes, and this is important because at what? Nothing at 5. And nothing, yeah. So I was talking to Rick about the advantages of board talks and computer talks, and one of the advantages of computer talks is that you only look like an idiot once in these things, because after someone corrects you, then you can, then you have them right in the future. OK, so yes, we have 2 particles at 1, 2 particles at 3, and 1 at 4, nothing at 2 and 5. And now I can do this in any order. So some of you might want to say, oh, we should start with the left first, and we should do this one first. Others might say we should do this one first. In distribution, this will not matter. The final distribution on what we get to at the next stage will be the same. And another thing we can do is we can do them all simultaneously. So in this case, let's have this one go 1 in each direction, this one, they both go to the left. And then what am I left with?
So the rule is that if you have more than one particle in the site, then all of them move?
We'll get to that in the next. So in the next state, no. So only two particles move, or pairs of particles move. So now what we get, so this particle disappears. Now we've got 3 at 2, none at 3, and 1 at 4. So hopefully I can get it right this time. And now Omer's question is relevant. What do we do when we have 3 particles and we only move 2 of them? So we always move an even number of particles. And then, so then this gets down to and we are back at the, so we did all that, we got back to the configuration we started with. So what did we learn about this Markov chain? We learned that this Markov chain is aperiodic, and it's also pretty easy to see that it's mixing. You can get from any state to any other state pretty quickly, and that's not too hard to see. And so then here, this is stable.
How come you had 5 originally and now have 4 only?
Yeah, so at this stage, yeah.
It's a boundary?
Yeah, so it's a sink. So at both boundaries, there's a sink.
Okay.
So here's my sink, which I didn't draw after the first state.
What is the rule that made both move to the left?
Yeah, every particle that moves independently, one step to the left or one step to the right. So sometimes they moved in opposite directions. Sometimes they moved jointly. Are there any questions about this Markov chain? About the definition of this Markov chain? I've got a lot of questions about the Markov chain.
So the Markov chain is adding a particle and stabilizing.
Yeah. So one step of the chain. So going from here to here is one step of the chain. So every step is one adding a particle and 2 stabilizing. Okay, so what would I like to know about this chain? Well, one thing that I would like to know is I could look at little dn, which is, so this is a aperiodic mixing Markov chain. It's got a unique measure of maximal entropy. I'll call that mu n. I'll look at the expected value of 1 over n times the summation I goes from 1 to n of little omega n. So I count the number of particles. I take the density of the number of particles. Here it's 4/5. And then I take the average over the invariant measure. And this, so for each n I get such a value. And then one question I have is, does this converge to some infinite value of d? And if it does, what is that value? Clearly, it's got to be something between 0 and 1. Is it strictly between 0? Is it strictly greater than 0? Strictly less than 1? That is a so both of those are non-trivial statements to show that those values are strictly 2?
D sub 2.
I don't know what d sub 2 is. I mean, I probably could figure it out, but yeah. But I'd want to write down the whole Markov chain and yeah, there aren't a whole lot of possibilities, but I do not off the top of my head know. I could figure out probably D1. That's probably an easier calculation, but I don't like to do new calculations in front of audiences, as, yeah, I've had enough practice doing that teaching. Okay, so, and then what other questions could you ask? This is a Markov chain, a family of Markov chains. You could ask, what's the mixing time of this Markov chain? You could ask, does it have cutoff? Any sort of typical Markov chain properties you could ask. Okay, now I'd like to explain why I'm interested in this chain. So, and what particular questions do I have? So the answer goes back to what Caroline was talking about this morning with the chip firing games, because this is a chip firing procedure, except I have, instead of her deterministic rules for chip firing, I have got a random rule. I much prefer a random rule to a deterministic rule, and I'm going to tell you why I prefer that now. So there was a paper written in the 1980s by Bach, Tang, and Weisenfeld about self-organized criticality, and they had a theory for how various different physical systems operated, and this is one of the most widely cited papers in physics. So how widely cited was that that one paper has about as many citations as Rick has in his whole career. So that's an impressive number. It's certainly way more citations than I have, but it's an impressive number. It's not among the very highest cited papers, but it's pretty close. And what did they talk about? So what's the self-organized criticality? So there's no density parameter in this system here, but what we see by adding in particles and then doing this stabilization is this Markov chain tends to a density, so this quantity here, with very high probability is close to some critical density. And so they said that this is characteristic of various things like avalanches, earthquakes, and so on. So why is this system here kind of supposed to be representing avalanche or earthquakes? Well, what I think of the particles as energy. And then so I have kind of competing things. I'm adding in energy, and then I'm dispersing energy. So I've got my, if I'm thinking of earthquakes, I've got my two plates here, and the plates start to move a little bit and move a little bit, and then that adds in a little energy, and then at some time that energy releases. And I could have it could either be a small release of energy. Just recently there was an earthquake in Seattle where I noticed that my wine glasses were shaking a little bit. So you could have just very small releases of energy, or you could have these very large releases of energy, like sometimes we get really bad earthquakes. Like 30 years ago, the Northridge earthquake here was a very devastating event. So you get kind of this whole range of different things. And so they said that systems like this were kind of somehow driven towards criticality without tuning some parameter. Now, what sorts of questions would we like to ask? Well, when I think of earthquakes, as I said, the range of energy in an earthquake goes over all scales. The Richter scale measures the logarithm of the energy because you can have very, very small earthquakes that you can feel, and then you can have these massive ones. So what would we like to know here? So here, I would like to know the number of firings. So this had, going in the first step, I had 0 firings because I had initially these 3 particles, and then I added 1 particle. The system was stable. So there were 0 firings the first time. The second time, when I added a particle in here, I fired this site. So at first I fired this site 1, but this 2, 3, and this 4. So I had 4 firings. So, and the second time I had 4 firings. So one thing that I would really like to show is that the probability under mu n of the number of firings greater than or equal to k is equal to k to the minus alpha times. So I have some power law for the number of firings. So this is a property that we would really like to know about in this system. And what else would I like to know about? I would also kind of like to know about the stable state. So I would like to know, here I looked at the expected density. Here I can look at the variance of the density. Well, I'll just look at the variance of the number of particles. I think that this should, well, physicists think that this should be into the beta where beta is less than 1. So if I just put down particles independently, then the variance would be n. So these particles are negatively correlated. That is one thing that the physicists would really like to see in this system. I don't have answers for any of these questions so far. And by the end of the talk, I still won't.
What's known about the sandpile in 1 dimension for these questions?
So if you do the abelian sandpile, so this model is called the stochastic sandpile. And if I do the abelian sandpile, I'm not sure for this model what is known about that. And what?
You don't know for the sandpile.
Yeah, I'm not sure. I mean, the results that I know about this sandpile are starting all the particles at the origin. I don't. So this version of the model is called driven dissipative. The driven is adding the particle, and then the stabilizing is the dissipative. And but I should know, but I do not know what the abelian sandpile results are for driven dissipative.
One thing that you could say is that you would know the number of fires. Like you can record the odometer function in that case.
Okay, so now I want to explain why I do not like the abelian sandpile model. So Carolyn showed all these beautiful pictures this morning. I do not like beautiful pictures for this reason. Those beautiful pictures appear because there's some very nice algebraic structure that same structure, which allows these beautiful pictures to appear, also mean that some of the predictions that physicists have do not materialize for the abelian sandpile model. And that's why I moved to a stochastic model, is because these are believed to have the properties that the physicists would like to see. So what's one thing? If I look at, so on this axis, I'll have time, and this axis, I'll have number of particles. There's something that's known as a hockey stick conjecture, so I'm going to start from the empty configuration and run this Markov chain. well, if I start from the empty configuration, then the stabilization is not going to do very much at the beginning. So I expect the number of particles to rise linearly. And then I get to some constant times n. And I expect it, I mean, it's going to be random, but it's going to look basically, like a 45-degree, that every particle that I add doesn't cause more particles to leave up until I get to some critical density. And after that, it's going to fluctuate around that critical density. This is called the hockey stick conjecture. And for certain models of the abelian sandpile, for certain graphs, it's been proven that the abelian sandpile model does not follow this conjecture. It goes above and then falls back down. And the physicists really would like to see this behavior. And they don't see that when there's a deterministic rule, but simulations indicate that for these random models that they get the behaviors they like. And yeah, so we saw a bunch. So one of the nice things about giving the last talk is that people have already kind of talked about these things. So we saw the beautiful work, the pictures for the abelian sandpile model in 2 dimensions, and the beautiful work of Levine, Pegden, and Smart. And that work shows this wonderful structure in lots of different areas of math, but it doesn't show what the physicists want. Now, unfortunately, I can't prove very much about the model that I described to you. I described this model to you because it has a simpler description, but it is one where, it's generally thought to, well, it generally has turned out to be more complicated to analyze than the one that I'm going to talk about now. So now I'm going to introduce the model that I'm going to be able to prove some results about, which is called activated random walk. So before we do that, are there any more questions about the stochastic sandpile model? Yeah?
When you spoke of mu, and I think when you introduced it, you spoke of it as a unique, you introduced it in the context of equilibrium, but then said it was the unique maximal entropy. So it's the unique invariant measure. I'm not sure if I said if I said maximal entropy, I didn't mean it. But it's easy to see that this is a mixing aperiodic Markov chain, so it's got a unique invariant measure.
So these exponents, alpha and beta, they're also supposed to be different than the abelian sandpile ones, or the same? They're not believed to be the same. So it should be this. So what physicists would like is a universal model. So we would like that kind of every reasonable model, that many varieties have the same exponents. But so far, for the stochastic case, we're a long way from knowing these exponents. Either of these exponents exist. Okay, so now I will describe activated random walk. So it's going to be a similar model. The main thing that the models people have used to describe self-organized criticality is that they all have some property that says if you have too much energy in a certain region, then there's a dispersal rule. So that dispersal rule could be that one particle goes one direction, one goes the next. It could be random. I'm going to now give you a different dispersal rule. And what is this? So my state space, I'm now going to have two types of particles. So my particle can either be awake or asleep. So what do particles that are awake do? These perform simple random walk. And the asleep particles stay put. Now, how can you move between these two states? Well, so
only 1% of people can solve this.
So awake particles. So each awake particle has a clock associated with it. It rings. So it can ring and it can give either of three instructions. It can say move left, it can say move right, or it can say fall asleep. So it moves left with rate 1/2, it moves right with rate 1/2, and it falls asleep with rate some rate lambda. And so that's how we can go from awake to asleep. And sleeping particles wake up when a wake particle arrives. A wake or active particle arrives. So my state space is going to be so I'm going to, at each site, I'm either going to have no particle or a sleeping particle when I have a stable configuration. So a stable configuration is one where all the particles are asleep. And this is contained in 0s. So if I have a number, a positive number, that tells me the number of awake particles at that site. So if there are two particles at a site, the clock rings for one of them. It says go to sleep. It goes to sleep, and then it's immediately woken up by the other particle at that site. So I can never have, if I have two or more particles at a site, they're all going to be awake. So are there any questions about this model?
So if you have two particles at a site, they can't happen to fall asleep at the same time?
No, yeah, so I work in continuous time, so only one action happens at a time. Yeah, so I'll have the same driven dissipative model where I have sinks at the end. And then everything does simple random walk. Why do I like this model? So why do I like this model? It turns out to be simpler to analyze because particles only move one, or can move one at a time, and that makes some analysis easier. The definition is a little more complicated. That's why I started out with the original example with the stochastic sandpile rather than the activated random walk. But they're widely believed that they should behave in the same way. Okay, so
You mean the same exponents, or?
I believe they should have the same exponents. But But what certainly should have the same exponents is if I look at activated random walk with different in different ways. So I could look at here. I had a finite line segment as my graph. I could now look at versions that are on the infinite line, and so I said that there was this theory of self-organized criticality. There have not been any very good mathematical formula, or there have not been that many very good mathematical formulations of self-organized criticality. And then back in the late 90s, early 2000s, this group, including Dickman, Munoz, Vespagani, and Zapperi, they came up with this explanation for self-organized criticality. And what did they say? They said that self-organized criticality consists of two things. It consists of a system that has a standard phase transition, and then it has a mechanism which guides the system to that. So let's see. So I have an infinite system. And here, so I start with some measure on my original system with at least some density of the particles, with not all the particles asleep initially. And then I can ask, does this system stabilize? So stabilization means that every site fires only finitely often. And it's pretty easy to see. So, boom. There exists some critical density such that if rho, which is my density of particles, if rho is less than rho critical, then the probability of stabilization is equal to 1. And if rho is greater than rho c, then the probability of stabilization is equal to 0. And this is
doesn't depend on the distribution of the particles?
So no, it does not depend on the distribution. It does not depend on the distribution of particles if all the particles are initially awake. So if and so this is a result of Liorola, Blattersitter-Vicious, and my memory is failing me on the last name, unfortunately. So no, it does not depend. So there's a very easy proof that if I take, say, just a Poisson row number of particles at every site, then I get this rho c. And that proof is just the abelian property. So suppose my system does not stabilize with rho is equal to a half. I put down a Poisson 1/2 number of particles and at every site, all of them active, and the system doesn't stabilize. Then if I put down Poisson 3/4, the system will not stabilize. How do I do that? Well, I just break my Poisson number of particles into 1/4 and 1/2. The 1/4 I just will never touch. Because of the abelian property, I can choose to do this in whatever order I want. So I'll just never move those particles. The Poisson 1/2 particles will go on. They'll never stabilize. So, and the abelian property says if the system doesn't stabilize under one set of operations, then the system doesn't stabilize under any set of operations. So if I if I raise my value of rho, so if I didn't have stabilization and I raise my value of rho, I'm not going to have stabilization. But then the remarkable thing is that this does not depend on the distribution. So it could be any independent distribution. It could actually be any ergodic distribution you want. So it doesn't even need to be. It doesn't need to be independent. So there exists this system where I have a standard phase transition. And then, so this claim of Dickman, Munoz, Vespagani, and Zeffirelli was self-organized criticality is realized by a system with a normal phase transition and then something with the driven dissipative thing which drives the system to the phase transition in the infinite system. And so they came up with what's known as the density conjecture. What does the density conjecture say? The density conjecture says that rho c is equal to the limit at, as n goes to infinity of dn, which was the density So this is the density in the driven dissipative system. And this is the critical value in the infinite system. Their conjecture was for the stochastic sandpile model, but it should hold for the abelian. Or for activated random walk as well. Yes?
Rho c doesn't depend on lambda?
Rho c does depend on, rho c depends on lambda. So I haven't said much about lambda, but so lambda can be anything from 0 to infinity. Lambda is equal to 0 says particles never fall asleep. This is the Prague model, so it's a well-known model. Lambda is equal to infinity is also a well-known model. So particles, as soon as they become the only particle at a site, they immediately fall asleep. That is IDLA. So kind of at the two extremes of activated random walk, I've got well-known models, the Prague model and IDLA, and this interpolates between these. And so this rho c is rho c of lambda, and it's been proven that this rho c goes to 0 as lambda goes to 0, and it goes to 1 as lambda goes to infinity. Okay, so are there there are questions about the density conjecture? Yes?
So which lambda is it for then?
So for any lambda, there exists this rho c, and I have I just have been failing to write in my lambdas for all these, but all these depend on lambda. Okay, so there's a kind of expanded version of the density conjecture. So one thing that Caroline talked about was in the abelian sandpile model, I started a lot of particles at the origin and then let it spread out and stabilize. I could do the same thing here. I could take the infinite graph, I could start in particles at the origin, and I could let it stabilize, and I could see how much this spreads out. So let's put 2 in particles at the origin. And then I could look and I could see the final configuration. So I want to look at the support of the final configuration. And what might I hope? I might hope half the particles go to the left, half the particles go to the right, and the density is rho, or this rho critical. So this is equal to minus n over rho c times 1 plus little o of 1 to n over rho c times 1 plus little o of 1. With and this is rho c, and it's rho c of lambda here. So this density that I get here, I start a bunch of particles at the origin, I let it stabilize, I get the same density. Another way I could do it is I could put particles on the cycle. So if I have density less than 1 in the cycle, it's always going to stabilize. But the question might be, how long does it take to stabilize? And what we see is that for low density, then the time it takes to stabilize is very quick. It's polynomial or linear time. And for high density, the time that it takes to stabilize is very large, and it's exponential. And the threshold, so an expanded version of the density conjecture is saying that the threshold happens at this same density rho c. So what Matt Junge and Toby Johnson and I were able to prove is we were able to prove this expanded version of the density conjecture for any value of lambda. So for any value of lambda, there's this rho c is strictly between 0 and 1. That's some results of a large group of people, and that this density. So the existence was known for the infinite system before these other three critical values for the driven distributive system, for starting the point source system of starting 2 n particles at the origin, and for doing it on the cycle. These critical values were not known to exist before, but we were able to show that they all exist, and all of these systems are equal. So Now, how do we go about doing this? So what we want to do is, so we don't know how to analyze any of these three systems to show there exists the phase transition directly. But what we do is we introduce a new system. And this new system, we are able to show that, and this new system we're going to introduce is going to be a super additive process. And we're going to show that it has a nice phase transition, and it's going to have some nice large deviation bounds. And then once we analyze this system, then we can show that the critical value for this is the same as the critical values for all these other systems. So that's the strategy that we have, and I've got 5 minutes left, so I could say a little more. So I'll say a little bit about how we try and prove this. So what we want to do, so we have two really nice properties in these abelian networks. So first we have the abelian property. We can do the toppling in whatever order we want. And the second is what's known as the least action principle. So what's the least action principle say? So there's something which is the number. So the odometer is the number of firings at each site. So the odometer at Z is the number of firings at Z. So it's a function, and it tells me, so I start with, say, 2 n particles at the origin, and then I stabilize. I say, how many times did a particle at site 1 fire? How many times did a particle at site 2 fire? And so on. Now, and then I want to look at what's known as the Diaconis-Fulton representation of this system. What is that? So I have a set of instructions at every site that says the first time that there's a particle at site 3 and it rings, it is going to move to the left. The next time a particle at site 3 rings, it's going to fall asleep. Then the next one is going to move to the left. And so I have this set of instructions. That's the randomness in my system. And then I can move particles, whichever particles I want, but just every time that I move a particle at site 3, I have to do the next instruction and then cross that one off the list. And then the next time I move a particle at site 3, I take the next instruction. And so now I can say for any function, so for any, well, I'll say any stable function f of z. What's a stable function? A stable function says, well, if I perform this number of instructions, f of 0 at 0, f of 1 at 1, f of 2 at 2, what I wind up with is I wind up with at most 1 particle at every site, and all the particles are sleeping. So for any stable function, I have that f of z is greater than or equal to the odometer at z for all z. So what can I do? So what is the strategy that we have? What we want to do, yes?
The definition of a stable function?
So the definition of a stable function is, no. this is the result here, is that for any stable function, the odometer is, the value for the stable function is going to be at least the odometer. But what the definition of the stable function was, if I apply f of z instructions at every z, so I know how many particles I initially have at 0. I've got 2n particles at 0. I do a million f of 0 is a million, so I do the first million instructions. It said that half a million moved to the left and half a million moved to the right, and there were a million sleep instructions. Then I want that at 1, I'm going to, so now I want to say the number of particles that move from -1 to 0, and the number of particles that move from 0 to, or from 1 to 0 has to either be, so I moved away all a million particles, so the number that moved from 1 to 0 plus the number of particles that move from -1 to 0 minus the number of particles that move away from 1, that's the total number of change of particles at the origin. And so that should, so then when I add in the initial number, that should give me either 0 or 1. And if it gives me 1, then the last instruction must be a sleep instruction. So since I am out of time, I chose not to write that down. Okay, but anyway, so it just says if we perform, so another way of thinking of this is I perform some number of instructions, and now I'm allowed to wake up sleeping particles. So now so you do some number of instructions at every site, that's f of z, where I'm allowed to wake up sleeping particles. So I can tell the sleeping particles to move, and I count how many instructions did I have. And a function like this is a stable function. Provided the final configuration I get to is stable, that's a stable function. And so what this is saying is that activated random walk or the stochastic sandpile or the abelian sandpile, they all have this property. They're very efficient at packing in particles, because any other way you do it, where you sometimes try and tell other particles to move, then tell sleeping particles to move, you're not going to wind up with a greater density. There's no way that you're going to kind of make the system dissipate energy less by telling sleeping particles to move. And so what we do is we use this new process that we introduced to construct a stable function. So that gives us some upper bound on what the odometer is. And then we also use this process to say that the odometer must be at least as high, so we can actually get some pretty tight bounds on what the actual odometer actually is. And we can do this for all values, for all values of lambda, including the critical value, and that is something that we had not been able to do before. So I'm few minutes over, so I'll quit here.